Okay, so finally, the very last part 4 of 4 in the series, Secrets of the Periodic Table. Ooh, secrets. Learn how to decode chemistry with your secret decoder ring of the periodic table. So we're going to be going over the size and shape of an atom, its electronegativity, and some other tricks to reading the periodic table that we didn't cover going over the ionic and covalent bonds in the previous sections of the series. So first, we're going to go over size. And usually when they talk about size, usually you're going to hear the term atomic radii, and that just means the radius of the atom. So if you remember your physics or your geometry, here's a circle, and all the way across the fattest part of the circle is the diameter. But if you cut that in half and you start from the middle point in the circle and you just measure 1/2 out to the edge of the circle from the center, that is the radius. So atomic radii would be the radius of the atom, and that includes the nucleus and the orbitals and the valence shell orbital that goes around the nucleus where the electrons orbit around. Now, if you look at the periodic table, as you go down the table and to the left, the size gets bigger, and I can explain to you why in these next couple of pages. So here's the periodic table, and the row number will give you an idea of how many orbitals it's going to have. For instance, in this row number 1 right here, this is for hydrogen, and it would have 1 electron on it because it's hydrogen and it only has 1 proton, 1 electron. And so, but if you go down the rows or the periods in the periodic table, there adds more and more orbitals around the nucleus to hold the more and more electrons it has. Because remember, the street address, the atomic number, here's 1, 2, 3, 4. This is the atomic number is the street address, but it also tells us how many protons are in the nucleus and how many electrons are orbiting around. So as you can see up here, in the lower right-hand corner, we have atomic numbers such as 115, 116, 117. So that means there's 115 protons in the nucleus, which means there's going to be 115 electrons orbiting outside the nucleus. So that's a lot of electrons. So we're only fitting, a certain amount of electrons, like 8 electrons at a time on each orbital, and then we have to create another orbital outside of that for the next set of electrons until we get all the way out to the valence shell orbital, which holds 1 to 8 electrons. Its very last set of 8 electrons in the atom. So as you go down the rows or the periods of the periodic table, you're going to be adding more and more orbitals around the nucleus because you're going to be having more and more electrons. And so that's going to make the atomic radii much larger than when we started out with, when we only had 1 orbital, 1 valence shell around because we only had 1 electron that we had to contain in an orbital around the nucleus. So as you go down the rows, the atom is going to get bigger because we're adding more and more orbits around the nucleus to accommodate the more and more electrons that these atoms are having. So the atom is going to get larger the more downward you go down these rows, down the columns, down the rows, the atoms are going to get larger. But, and here's what trips some people up. If you go to the left on the columns of the periodic table, the atom is also going to be bigger. Why? Well, because there's going to be more space between the orbitals, and each orbital is going to have more space between it, and there's going to be more space between the center orbital and the nucleus. Because if you go the other way, as we established before, going to the right, the street address is going to get bigger, that atomic number. So it goes from 1 to 2, and then the next period, we go 3, 4, 5, 6. And this is not only the address, it's telling us how many protons are in the nucleus. And it's not only telling us the address and how many protons are in the nucleus, it's also telling us how many electrons are outside of the nucleus because we always have to keep the same number of electrons that we have protons, right? So we're getting more and more electrons as this build up and more protons in the nucleus as this progresses to the right. And remember the column rule. These columns, this 1, 2, 3, 4, and so on, that's telling us how many electrons are in the valence shell. So as we progress over to the right, not only are we gaining protons in the nucleus, but there are going to be more and more electrons in that outermost shell, the valence shell. And so these electrons and protons, the positives and negatives attract each other, right? So these electrons in the outside valence shell are going to be more and more pulled in towards the nucleus, and it's going to start compacting in on itself, these atoms. So even though it started out like this size, it's going to, as we go to the right, it's going to get smaller and smaller. The valence shell is going to get tighter and tighter around that nucleus because of magnetic attraction until we end up having a maybe a little bit larger of a nucleus to accommodate all the new protons we put on there. But all these extra additional electrons that are in the valence shell made the valence shell magnetically get pulled towards the nucleus and thereby shrinking the atom's radius. And so you end up getting smaller, even though you have more protons and more electrons, more valence electrons in the atoms on the right. It actually turns out to be a smaller atom because it kind of compacts in on itself because of the magnetic pull towards the center. So you're going to be going to get the bigger atoms, the smallest is going to be up in the upper right-hand corner, and then we're going to go down and to the left to get to the biggest atoms are going to be in the lower left-hand corner. And let's look at that first picture again that I drew with the atom. See how when we go down, as we go down, the atoms add more orbitals and it gets bigger down here, bigger. So it's bigger at the bottom and it's going to be bigger on the left because by the time you get to the right-hand side, it's compacted in on itself. So the smallest starts in the upper right-hand corner and the biggest ends in the lower left-hand corner of an atom's radii. Now, number two, the reactivity. The reactivity of an atom is the ability to form bonds or turn into ions. So it's how reactive it gets. It's how easily it ends up having a chemical reaction. So reactivity, reaction. How easy is it to have a chemical reaction with this atom? And it's the result of combined electronegativity and ionization energy and the affinity. So the electronegativity, and this is very important to pay attention to because this electronegativity, knowing this about electronegativity, is going to help you with a lot of stuff later on down the road. Maybe not this semester so much, but the second semester and down the road, it's all about electronegativity. When you get into organic chemistry, it's all about electronegativity. So electronegativity is how easily it attracts electrons. It's how much of a magnetic pull it has for the electrons, so all the electrons start kind of migrating over there. That's electronegativity. Ionization energy is how easily it loses electrons. So these two things are just polar opposites from each other. Electronegativity is how much it attracts electrons. Ionization energy is how much it gives away electrons, it loses electrons. And then affinity is the amount of the energy change. And remember, this little triangle means the amount of change. So the energy change when the atom gains an electron. So when the atom gains an electron, that energy that was stored that is now used up and done has to go somewhere. So it just gives off a bunch of energy when it attracts another electron. So that amount of energy that it gives off when it gains an electron is called the affinity. And now this is the one that it's not just across the board. It's different when it's metals between nonmetals and metals. When it's metals, the reactivity, the increased rate of their ability to form the bonds or to turn into ions increases as you go down and to the left, just like the atomic size that we were just doing in the previous one. But that's only for metals, the ones on the left side of the periodic table. The nonmetals have an increased reactivity and increased rate of reaction when you go up and to the right. So it kind of looks a little bit like this. So this purple, this is the reactivity. So in the metals section, here's the metals section. In the metals section, the least reactive metal is going to be up here on the upper right, and then it's going to be more and more and more reactive the lower you go and the more to the left you go. So the most reactive metal is going to be the francium. In the nonmetal section over here on the right tower, remember we called these the two towers, the nonmetals is going to start in the upper right-hand corner with the most reactive nonmetal, and that's going to be the most reactive. So the least reactive is going to be down here in the left-hand corner, and it's going to get more and more reactive the more towards the right it goes and the more up the column it goes to the top of the page, to the top of the table. And that's for nonmetals. So see, for metals and nonmetals, it's two different things on the periodic table. You just have to remember that. And the electronegativity, the most electronegativity is going to be also in the upper right-hand corner, this fluorine, and the least electronegative element is going to be this francium in the lower left-hand corner. Okay, so number three, metallic character. So metallic character is pretty much measured by its ability to conduct electricity because you know is a great electricity conductor. And the least metallic character is going to be up in the nonmetals at the top of the periodic table, of course, because these are where the nonmetals are. So of course that's going to have the least metallic character. And the metals are over on the left. So of course, the more further left you go on the periodic table, the more of a metallic character you're going to have from that element. And also the more you go down the column in the periodic table to the bottom, the more metallic character you're going to have. So that's going to look like this. See, the least is up here, least metallic, and then you go down into the left, and then you get to the most metallic. So this is going to be, this francium is going to have the most metallic properties. So this is going to be the best conductor of electricity. So best electricity conductor. Now, number four is the melting and boiling points of things, because we know that water boils at 100 degrees, but that's just water. Everything has all different melting and boiling points. Snow melts at 32 degrees Fahrenheit or 0 degrees Celsius, and then it turns into water, and then it boils at 100 degrees. So everything has its own melting and boiling point, and it's really based on how strong the bonds are connecting the atoms that are all bonded together, making the molecule. So the stronger the bond, within that molecule is going to have a higher melting point and a higher boiling point, which means you're going to have to get it hotter in order for it to change phases. Now, in columns 1 through 4, this is supposed to be a 4, in columns 1 through 4, you're going to have the lowest melting point is going to be the bottom left-hand corner, and it's going to go up to the top right-hand corner in the fourth row, or in the fourth column. But then it changes. Once you get to the fifth column, the melting and boiling points drop a little bit, and then they kind of just plateau and they stay that same kind of low, and they stay that same in this within that same area all the way over to the eighth column. So that's going to look a little bit like this. So see, as you go from 1 to 4, your melting and boiling point is going to get higher. And here is up to 4, it's going to get higher. So higher melting point and boiling point because these have stronger bonds. But then as soon as you get up to column 5, for some reason, it drops. It goes down, the melting point and boiling point goes down and gets colder, so you don't have to warm it up as much as you need to do with other things in order to get it to melt or boil. And then it just sort of plateaus until you get over here to column 8. And that's it. So thanks for bearing with me for all this 4-part series. But I'm telling you, if the teachers forget to teach this stuff because they're just so used to knowing this, they forget that if you're an introductory student coming into chemistry for the first time, you haven't been taught this and you don't know this. So a lot of times it's forgotten to get taught in your classes. So this is why I wanted to do this series on the secrets of the periodic table and how to really read this periodic table, because it will give you a lot of the answers that you're getting confused on if you know how to read this thoroughly.